we'll start with a new chapter of Standard 11th, that is chemical bonding and molecular structures. So chemical bonding, basically it tells you about the bonding between two elements or two atoms. Okay, so you know that about matter I think you have studied in your 9th standard. Okay, matter is a thing, a substance that has mass and occupies space. So every matter is made up of one or different types of elements. Okay, so under normal conditions, no other element exists as an independent atom in nature. So under normal circumstances, you cannot find any single atom to be existing. Okay, they either exist in their double form like H2N2, or they can exist in the form of combination of two different atoms. For example, water. Okay, water consists of hydrogen and oxygen. Okay, now except noble gases. Okay, noble gases can be found in their single form. Now, however, a group of atoms is found to exist together as one species having characteristic properties. So we have observed that there are molecules with two different elements. They can exist together, showing one particular characteristic. Now, such a group of atoms is called a molecule. Okay, so this is called a molecule. Now, obviously, there must be some forces which holds these constituent atoms together in the molecule. As you know, a molecule is made up of two or similar or two different atoms together. So there must be some kind of force or some kind of connection between these two atoms, right? That's why they are held together. Now, the attractive force, okay, which holds the various constituents, okay, constituent like atoms and ions together in different chemical species is called a chemical bond. Now, what is a chemical bond? It is an attractive force which holds different types of atoms or ions together to form a different chemical species is called a chemical bond. Okay. The formation of chemical compounds takes place as a result of combination of various elements in different ways. Okay, so chemical compounds, they are formed by combination of atoms. Okay, combination of various atoms of various elements in different ways. Now this gives rise to some questions like, why do atoms combine? Okay, why do they combine? What is the need to combine? Okay, why are only certain combinations possible? First of all, why do they combine? Second thing is, if at all they are combining, why do they combine with certain elements only? Why don't they combine with other molecules or other atoms? Okay, another question is, why do molecules possess definite shape? Why do they have a fixed shape? Okay, now to answer these questions, okay, different theories and concepts have been put forward. Okay, now I've asked, now there are many questions given here, like why do they form, why do atoms combine, why do they combine only with certain molecules or certain atoms, why do they have a definite shape? So to prove or to answer these questions, there are certain theories and concepts which are put forward. So in this chapter we will basically learn those theories and those approaches. So here first you have this Kössel-Lewis approach, valence shell electron pair repulsion theory, that is VSEPR theory, valence bond theory, that is VBT, molecular orbital theory, that is MOT. So these are the theories and concepts that you will be learning in this chapter. Okay, and this gave rise to the evolution of various theories of valence and interpretation of nature of chemical bonds have closely been related to the development in the understanding of the structure of atom, the electronic configuration of elements, and the periodic table. Okay, now all these concepts, they are related to their structure, okay, structure of that atom, their electronic configurations, and periodic table. Now structure of atom we have seen, electronic configuration also we have done, periodic table also we have seen. Now depending on them, these theories and concepts are given. Okay, now every system tends to be more stable and bonding in nature's way of lowering the energy of the system to attain stability. So every system, they eventually want to attain a stable form. Okay. Now, first we will start with Kössel-Lewis approach of chemical bonding. Okay. What did Kössel-Lewis do? Now, in order to explain the formation of chemical bond in terms of electrons, a number of attempts were made, but it was only in 1916 when Kössel-Lewis succeeded independently in giving a satisfactory explanation. Okay, so there were many explanations which were given for the formation of chemical bonds in terms of electrons. Okay, and a number of attempts were made, but finally in 1916 Kössel-Lewis they succeeded independently. Okay, they didn't do together. Okay, they did separately, but they succeeded independently in giving a satisfactory explanation so as to why the bonds are forming. Okay, now they were the first to provide some logical explanation of valence, which was based on the inertness of noble gas. Okay, they were the first to provide a logical or a explanation which seems to have some point in it. Okay, regarding the valencies. Now, Lewis pictured the atom in terms of a positive charged kernel, the nucleus plus the inner electrons, and outer shell that could accommodate a maximum of 8 electrons. Now, what did Lewis pictured of an atom? He considered the center part, that is nucleus. Okay, he called this nucleus as kernel, and this kernel is consist of nucleus. Nucleus means your protons and neutrons, plus some inner electrons. Inner electrons means the ones which are close to the nucleus. Okay, together they are called as kernel, and an outer shell. Okay, he considered an outer shell. There is an inner shell and an outer shell. Okay, outer shell, he said that outer shell can accommodate a maximum of 8 electrons. Okay, now he further assumed that these 8 electrons occupy the corners of a cube which surround the kernel. Later what he said, कि all these 8 electrons, they occupy the corners of the cube. Okay, if we draw a cube, okay, this is a cube. If I draw a cube, what Lewis said is what he further assumed is the 8 electrons. Okay, these 8 electrons, they occupy the corners of the cube. Okay, 1 2 3 4 5 6 7 and 8. Okay, so electrons occupy the corners of a cube which surrounds the kernel. So at the center is your kernel, and around the kernel in a cube format the 8 electrons are occupied. Thus the single outer shell electron of sodium would occupy one corner of the cube, while in case of noble gases all the 8 corners would be occupied. Now, in our previous chapter we have seen electronic configuration of sodium. In that there is ns1, one electron is remaining in the s orbital of the last shell, right? So that one s orbital will occupy, that one electron will occupy one of the corner of the cube, whereas for noble gases, since they have a completely filled electronic configuration, they will occupy all the 8 spots of the cube. Okay, now this octet of electrons represents a particular stable electronic arrangement. Okay, since it is an 8 electron, we call it as octet. Okay, octet of electrons, they show a stable, particularly stable electronic arrangement. Since they occupy all the 4 corners, they are away from each other also, and they are equally distributed around the kernel, that is your nucleus also. Okay, so it is a particularly stable electronic arrangement. Now Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. Now, what did Lewis postulated? He postulated that atoms, they achieve a stable octet, okay, when they are linked by a chemical bond. Okay, in case of sodium and chlorine, this can happen by the transfer of an electron from sodium to chlorine, thereby giving Na plus and Cl minus ions. Now, why sodium and chlorine? Sodium has one electron in its last shell, whereas chlorine requires one electron to complete its electronic configuration. So the sodium will transfer that one electron from itself to chlorine, where chlorine will be satisfied and sodium will also have a completely filled octet. Since sodium is giving an electron, it will turn into positive, and since chlorine is accepting an electron, it will turn into a negative ions. Now, in case of other molecules like Cl2, HF2, Cl2, H2, F2, etc., the bond is formed by sharing of a pair of electrons. Now, NaCl, it is like transferring an electron, whereas when you have diatoms like Cl2, H2, F2, there you are sharing an electron. Okay, sharing of pair of electrons between the atoms takes place. Now, in this process, each atom attains a stable outer octet of electrons. Now, overall, what it does is, in this process, overall, the atom attains its stability by completing the octet. Octet means by completing the 8 electron in the last shell configuration. Okay. Now, next we have is the Lewis symbols. Now, in the formation of a molecule, only the outer shell electrons take part in the chemical combination, and they are known as valence electrons. Okay, the ones which are in the outer shell electrons, which are on the last shell, we call them as valence shell electrons or valence electrons, right? I've told you about this in our previous chapter. Now, the inner shell electrons are well protected and are generally not involved in the combination process. This also you know, because the inner shell electrons, they are well protected by the nucleus. So, nucleus will hold them tightly towards itself, and it is difficult to remove those electrons, whereas the ones which are present on the outer shell, okay, there will be less shielding of the electrons, there will be more shielding, okay, which will make it easy to remove that one electron from the outer shell. So basically, the electrons which are present on the valence shell or the outer shell are the ones which are involved in the bond formation or a combination. Inner shells doesn't take part in that. G.N. Lewis, an American chemist, introduced a simple notation to represent valence electrons in the atom. So here Lewis showed a simple, he is an American chemist, he introduced a simple notations, okay, to show the valence electrons in an atom. These notations are called as Lewis symbols. For example, the Lewis symbol for the element of second period are as under. So these are the valence shells of the second period. Now, lithium is atomic number 3. If I write the electronic configuration, it will be 1s2, 2s1. So in 2s there is only one electron, that is the valence electron of lithium. So 1. Beryllium is 4, right? So it will have 2s2. So the last shell has 2 electrons, so 2. Similarly, as we go on further, we will have boron 3, carbon 4, nitrogen 1, 2, 3, 4, 5, hydrogen 6, oxygen 6, fluorine 7, and neon 8. Neon is the complete one, okay, with 8 electrons in the valence shell. The significance of Lewis symbol. What is the importance of Lewis symbol? Now, the number of dots around the symbol represents the number of valence electrons. Since you can show the valence electrons with dots, that dots represents the number of valence electrons associated with that atom. Now, this number of valence electrons helps to calculate the common or a group valency of the elements. Now, this dot will help you to calculate the number of valence electrons. How many number of bonds can be formed, or how many number of electrons are required to complete the octet or the valence. What is the valency of that atom? Now this group valency of element is generally either equal to the number of dots in Lewis symbols or 8 minus the number of dots or valence electrons. So you can calculate it by looking at the number of dots. If there are 4 dots, that means the valency is 4, or the number of dot minus 8. Okay, 8 minus the number of dot. Okay, that will give you the valence electrons, number of valence electrons. Now next is your Kössel in relation to chemical bonding drew attention to the following facts. What are the facts that are associated with Kössel's approach? Okay, now in the periodic table, the highly electronegative halogens and highly electropositive alkali metals are separated by the noble gases. Okay, now when you see a periodic table, okay, this is your periodic table, right? Here you have your highly electronegative halogen groups, and here you have your highly electropositive alkali metals. Now both of them are separated by the noble gases, which are just after the halogens. Okay, so this is the first point that Kössel had said, ki the highly electronegative halogens and highly electropositive alkali metals are separated by noble gases. Now second one is the formation of a negative ion from a halogen atom and positive ion from an alkali metal atom is associated with the gain and lose of an electron by the respective atoms. Now here, formation of a negative ion, when negative ions are formed by the gain of electrons, whereas positive ions are formed by the loss of an electron. So the negative ions, okay, which are formed by the halogen atoms, and the positive ions which are formed by the alkali metals, they are associated with the lose and gain of the electrons, okay, by that respective atom. So halogens will gain electron, alkali metals will lose electrons. Third one is the negative and positive ions thus formed attain a stable noble gas electronic configuration. The noble gases, with the exception of helium, which have a duplet of electrons, have a particularly stable outer shell configuration of 8, that is octet electrons. Now when there is gain or lose of electrons and formation of negative and positive ions, okay, whenever there is a negative and positive ions formed, they attain a stable noble gas configuration. Okay, for example, your sodium, okay, sodium, when it remove that one electron, what will happen? All the previous shells are completely filled. By removal of that one electron, sodium will attain a completely filled octet, whereas chlorine, it requires only one electron to complete its electronic configuration. So by taking that one electron, chlorine is completing its octet, attaining its stable form or the noble gas configuration. Okay, so this is what the negative and positive ions, when they lose or gain electron, they attain a noble gas electronic configuration. Now noble gases, with an exception of helium, because helium is 1s2, okay, with an exception of helium, all the other noble gases, they attain an outer shell configuration of 8 electrons. Okay, they all have an outer shell configuration of 8 electrons or the octet electrons. Okay, now next is the negative and positive ions are stabilized by electrostatic attraction. So how the negative and positive ions are stabilized? They are stabilized by electrostatic attraction. So Na plus and Cl minus, they are attracted by electrostatic attraction or force, electrostatic force. They are attracted towards each other, and when they are attracted towards each other, they tend to stabilize each other. Okay, now here they have given an example. Okay, here again the same example, that is NaCl is given, sodium and chlorine. Now according to the above scheme, okay, whatever we discussed above, Na, what it does, it loses one electrons and become Na plus. Okay, now once it loses its electron, Na attains a stable configuration of neon. Okay, Now chlorine, what it does, it takes up the electron and becomes Cl minus. Again, when it takes that one electron and converts into Cl minus, it attains the electronic configuration of argon, which is again a noble gas. Okay, so sodium attains an electronic configuration of neon, whereas chlorine attains an electronic configuration of argon. Now you have Na plus and Cl minus. They are two different ions, and there is the electrostatic force of attraction which takes place in between them, and they form a NaCl or Na plus Cl minus ions. Similarly, the formation of CF2, that is calcium difluoride. Again, calcium, what it does is it loses 2 electrons. Okay, when it loses 2 electrons, it attains the electronic configuration of argon. Okay, this is the actual electronic configuration of calcium. Okay, by losing these 2 electrons, it attains the electronic configuration of argon. Now, fluorine, it takes up 1 electron. This is the electronic configuration of fluorine. It requires only 1 electron to fill the p orbital. So it takes up the 1 electron and it attains the electronic configuration of neon. Okay, since you have 2 ions, okay, 2 electrons that are taken out from calcium, you can take 2 fluorine molecules to satisfy both of the electrons. So it becomes CaF2. Okay, now the bond formed as a result of the electrostatic attraction. Okay, the bonds which are formed due to the electrostatic attraction between positive and negative ions was termed as electrovalent bond. Okay, those bonds are known as electrovalent bond. Now the electrovalency is thus equal to the number of unit charge on the ion. Okay, now the electrovalency is thus the equal number of unit charge. Okay, what is the charge on both the ions is what the electrovalency is. Now thus calcium is assigned a positive electrovalency of 2, while chlorine a negative electrovalency of 1. Okay. Now, Kössel's postulations provide the basics for the modern concepts regarding ion formation by electron transfer and formation of ionic crystalline compounds. Now, whatever Kössel's postulations are, they provided a basic modern concept, okay, regarding the information or regarding the formation of ions by electron transfer and formation of ionic crystalline compounds by electrostatic attraction. Now, his view have proved to be great value in the understanding and systematization of ionic compounds. Now, whatever Kössel had given, okay, it was of great importance. Okay, it has a great value in understanding the concept of ionic compounds. Okay. Now, at the same time, he did recognize the fact that a large number of compounds did not fit into these concepts. Okay, even though his postulations or whatever theory he had given was considered to be of great importance, but he himself had recognized that there are some molecules or some compounds which do not fit in his concepts. Okay, whatever concept he gave, in that concept there are some molecules which doesn't fit. Now, next is the octet rule. Octet rule. Now, Kössel-Lewis in 1916 developed an important theory of chemical combination between atoms known as electronic theory of chemical bonding. Okay, so what they did was the study between electrons. What happens when electrons are transferred here and there. Okay, so their study was basically on the basis of electronic or electron transfer or electronic theory. Now, according to this, atoms can combine either by transfer of valence electrons from one atom to another, that is gaining or losing, or by sharing of valence electrons in order to have an octet in their valence shell. Now, what does this theory means, or what does electronic theory of chemical bonding means? This means an atom, it can combine either by transfer of valence electrons. Okay, you can either transfer the valence electrons from one atom to another atom. Now, this means you can gain or lose electrons, okay, one atom loses, other atom gains. So gaining or losing of electrons, or you can form a bond by sharing of valence electrons, okay, in order to have an octet in their valence shell. Now this is known as octet rule. Next is a covalent bonding. Okay, next is a covalent bonding. Now, Langmuir in 1919 refined the Lewis postulations by abandoning the idea of the stationary cubical arrangement of the octet and by introducing a term covalent bond. Now what Langmuir had done, he refined or he re-edited the Lewis postulations, and in that postulation what he did is he cancelled the idea of stationary cubic arrangement. He said ki the arrangement of electrons, okay, it is not like a cubical form now of the octet, but and he introduced another term called as covalent bond. Okay, he deleted the concept of stationary cubical arrangement and he introduced a term called as covalent bond. Now the Lewis-Langmuir theory can be understood by considering the formation of the chlorine molecule. Now how you can understand the Lewis-Langmuir theory? Here they have done it with respect to Cl2, that is chlorine molecule. Now the Cl atom with electronic configuration Ne3s2 3p5 is one electron short of the argon configuration. As you know, chlorine requires one electron to complete its electronic configuration or octet, right? Now the formation of Cl2 molecule can be understood in terms of the sharing of a pair of electrons between the two chlorine atoms, each chlorine atom contributing one electron to the shared pair. Okay, now here what they did, they showed a sharing of electrons between Cl2 molecules. Now formation of the Cl2 molecule, we can understand it in terms of sharing pairs of electrons between two atoms of chlorine. Now here you can see this is Cl with 1 electrons in their valence shell. Now both of those 1 electrons, what they did is, now this is Cl 1 2 3 4 5 6 7. Okay, now here I'll show another Cl. Okay, 1 2 3 4 5 6 7. These electrons, they shared the electrons with each other. Okay, they shared the electrons with each other. Now if I count, this electron can be counted with this Cl also, this electron can be counted with this Cl also. So this is the sharing of electrons. Okay, sharing of pair of electrons. There are two electrons, so it will be pair of electrons. Now here also the chlorine is completing its 8 electron octet. Now in the process, both the chlorine atom attains the outer shell octet of the nearest noble gas, that is argon. So in this process, both of them are obtaining a nearest noble gas configuration. Now the dots represent electrons. Such structures are referred to as Lewis dot structures. Okay, those dotted structures, they are called as Lewis dot structures. Now Lewis dot structures can be written for other molecules also, in which the combining atoms may be identical or different. Now the important conditions being that, now Lewis dot structure you can use for other molecules also, like same identical molecules H2N2 F2. Okay, you can use them for identical molecules also, or the molecules with different atoms also. Now what are the conditions to be followed for writing them? Each bond is formed as a result of sharing of an electron pair between the atoms. It should show bonds which are formed, it shows the bonds which are formed as a result of sharing of an electron pair between the atoms. Now each combining atom contributes at least one electron to the shared pair. Here you have to show each electron. So the atoms in electrons in each atoms should contribute at least one electron. Okay, atoms which are involved in that molecule, they should at least contribute one electron to the shared pair. The combining atoms attain the outer shell noble gas configuration as a result of the sharing of electrons. Now here the combining atoms, okay, they should attain the outer shell noble gas configuration. Okay, they will attain an outer shell noble gas configuration as a result of the sharing of electrons. Now, thus in water and carbon tetrachloride molecule, formation of covalent bonds can be represented as. Now here hydrogen will complete its shell by taking one electron, that is 2 electrons each. Oxygen is completing its octet, again hydrogen. Here also all the chlorine molecules are completing its octet. Similarly carbon is also completing its octet, 2, 4, 6, 8. So all the molecules are completing their octet forms. This is by sharing of electrons or forming a covalent bond. Thus when two atoms share one electron pair, they are said to be joined by a single covalent bond. Okay, thus when we say that two atoms, they are formed by sharing one electron pair, okay, that they are said to be joined by a single covalent bond. Now in many compounds we have multiple bonds between atoms. Okay, many compounds have multiple bonds between atoms. The formation of multiple bonds envisages sharing of more than one electron pair between two atoms. Okay, now when we say multiple bonds involve sharing of more than one electron pairs between two atoms. A single bond is involved with sharing of two electrons, then multiple bonds will involve sharing of multiple electrons. Okay, now if two atoms share two pairs of electrons, the covalent bond between them is called double bond. If two atoms A and B, okay, they are sharing total of 4 electrons with each other, that means they are forming 4 electrons, in the sense 2 pairs of electrons, that means they are forming a double bond. Okay, covalent double bond. Now for example is your carbon dioxide, CO2. Okay, it forms a 2 pairs of electron, forms a double bond with carbon, forms a double bond with both of the oxygen. Okay, similar with your ethene molecule. Now, when combining atoms shares 3 electron pairs, as in case of two nitrogen atoms, in N2 we call it as triple bond. Okay, when there is a sharing of 3 electrons or 3 electron pairs, we call them as triple bond. And here another example is your ethene molecule. This is your ethene molecule. Now Lewis representation of simple molecules or the Lewis structure. Now the Lewis dot structure provide a picture of bonding in molecules and ions in terms of the shared pairs of electrons and the octet rule. So Lewis dot structure, they provide a picture of bonding in molecules and ions. Now this is in terms of shared pair of electrons and the octet rule. Okay, while a picture may not explain the bonding behavior of the molecule completely, it does help in understanding the formation and properties of a molecule to a larger extent. Even though this can explain the bonding between molecules and ions, but they are probably not able to explain, or they may not be explaining regarding the bonding and the behavior of the molecule completely. Now, writing Lewis dot structures of molecules is therefore very useful. The Lewis dot structure can be written by adopting the following steps. Lewis dot structure is, though it is very useful, but it cannot explain some concepts. But what are the process of writing or steps involved in writing the Lewis dot structure? Now, the total number of electrons required for writing the structure are obtained by adding the valence electrons of the combining atoms. For example, in the CH4 molecule, there are 8 valence electrons available for bonding, 4 from carbon and 4 from hydrogen atoms. Okay, now how you will write the electrons, okay, required for the total number of electrons which are required for writing the structure, okay, for Lewis dot structure, how many electrons are required, okay, how to write those structure. They are obtained by adding the valences of the electrons of the combining atom. For example, carbon and hydrogen. Okay, carbon has 4 electrons in the valence shell. Okay, its last shell has 4 electrons. Now, to satisfy these 4 electrons, another 4 electrons should be added. Those are added by 4 hydrogen molecules. For 4 hydrogen, 5, 6, 7 and 8. 8 electrons in total. Okay, 4 from the carbon, 4 from the hydrogen. For anions, each negative charge would mean addition of 1 electron. So for anions, each negative sign will represent the addition of 1 electrons. Now, minus means there is addition of 1 electron. 2 minus, addition of 2 electrons. 3 minus, addition of 3 electrons. Okay, so the number of negative sign, okay, number of negative charge tells you the number of electrons that are added. For cations, similarly, for cations it will be the number of electrons that are removed. Okay, number of electrons which are lost, or the removal of number of electrons from that molecule. If 2 plus means 2 electrons are removed, 3 plus means 3 electrons are removed. As how negative ions, addition of electrons, similarly positive ions, removal of electrons. Now how many are removed, we can tell it by either the numbers which are given with their charges. Now for example, for CO3 twice 2 minus ions, the 2 negative charges indicate there are 2 additional electrons than those provided by the neutral atom. So this 2 minus means this CO3 molecule has 2 extra electrons in them compared to their neutral atom. NH4 plus means 1 electron is removed from the neutral atom. Okay. Now, knowing the chemical symbols of the combining atoms and having knowledge of the skeletal structure of the compound known or guessed intelligently, it is easy to distribute the total number of electrons, as the bonding shared pairs between the atom is proportional to the total bonds. Okay, now if you know the chemical symbol of that combining atom, for example, carbon dioxide, you know carbon and oxygen are involved. And if you know the skeletal structure means what is the electronic configuration. With electronic configuration you can tell what are the valence shell electrons. And if you know the skeletal structure of the molecules along with its chemical symbols, it is easy for you all to distribute the electrons, okay, as a bonding pairs. How many electrons are required for bonding, okay, how many bonds are formed, okay, that you can easily detect if you know the chemical symbol and the skeletal structure of that molecule. Now in general, the least electronegative atom occupies the central position in the molecule of iron. So the one with less electronegativity, it occupies the central position. For example, NF3, CO3 2 minus. Okay, nitrogen and carbon are the central atoms because both of them are less electronegative, whereas fluorine and oxygen are comparatively higher in their electronegativity and occupies the terminal positions. After accounting for the shared pairs of electrons for single bonds, the remaining electron pairs are either utilized for multiple bonding or remain as the lone pairs. So after accounting the shared pairs of electrons, okay, after showing the shared pairs of electrons, whatever electrons are remaining which doesn't involve in the bonding, they are known as okay, single bond, the remaining electron pairs are either utilized for multiple bonding or remain as lone pairs of electrons. Either those electrons can be used for multiple bonds or they can be kept like that, and we call them as lone pairs. Now the basic requirements being that each bonded atom gets an octet of electron. Okay, now what is the, you can keep it like lone pairs also, you can form multiple bonds, but eventually you should get a octet of electrons. Next is formal charge. Now what is a formal charge? Lewis dot structure in general do not represent the actual shape of the molecule in case of polyatomic ions. Now the net charge is possessed by the ion as a whole and not as a particular atom. Now it is however feasible to assign a formal charge on each atom. So Lewis dot structure, it in general doesn't represent actual shape of the molecule, doesn't give you the shape of the molecule. Okay, now in case of polyatomic ions means when there are many atoms involved. So the net charge, overall charge, is possessed by that ion as a whole and not by a particular atom. Okay, so the overall charge is by entire molecule, entire atoms present in that, but not by the one atom. Okay, now, however, it is however feasible to assign a formal charge, okay, on an atom. So you can give a formal charge, comparing all the charges, you can give a formal charge on the molecule, and you can give the subcharges to the atoms also. A formal charge of an atom in a polyatomic molecular ion may be defined as the difference between the number of valence electrons of the atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. So how you will calculate the formal charge? Okay, formal charge on an atom in a Lewis structure, you can calculate it by, if you know the total number of valence electrons in the free atom, okay, minus total number of ions, total number of non-bonding electrons, that is lone pairs of electrons, minus half of total number of bonding or shared electrons. Now I'll explain that part with an example. For example, let us consider ozone. Okay, O3. Ozone is O3. Now the atom have been numbered as 1, 2 and 3. Okay, for the central oxygen atom marked as 1 for this oxygen atom. Okay, now what is the formula? Formula is total number of valence electrons in the free atom. Okay, so oxygen, how many valence electrons does oxygen has? Oxygen has 6 valence electrons around it. This is a single free atom. Okay, so you should know when that atom is present singly in a free form, how many valence electrons does it has? Okay, so it has 6 valence electrons in it, minus total number of bonding, non-bonding, lone pair electrons. So here, how many non-bonding electrons are there? 2 non-bonding electrons are there. So minus 2, minus half of total number of bonding or shared electrons. So how many shared electrons are there? 1, 2, 3, 4, 5 and 6. Sharing is happening, right? So both the electrons we have to consider. Okay, so how many bonds? 1, 2, 3. 3 bonds means 6 electrons are involved. So 6. So by calculating it, you get a plus 1 charge. Okay, so the charge on this oxygen is plus 1. Similarly, you have to calculate for other molecules. Now here, total number of lone pair electrons or valence electrons in oxygen, again it will remain 6. How many lone pairs are there on the second carbon? We have 4 lone electrons. Okay, 4 unpaired electrons. 4 minus half of, how many bonded electrons are there? Since there are 2 bonds, you have total of 4 electrons. It will give you a 0. So the charge on this oxygen is 0. Similarly, charge on this oxygen is minus 1. Okay. So this is how you calculate the formal charge on each of the molecule. Now here you have to note that formal charges, they do not indicate the real charge separation within the molecule. Okay, this is just an assumption or a simple calculation to understand what will be the charges present on those molecules. Okay, now formal charges help in the selection of lowest energy structure from a number of possible Lewis structures for a given species. Now why we use formal charges? Formal charges, they help us in selection. There are various structures for each molecule. Okay, now formal charges will help you to select the one with lowest energy structure. Okay, now generally the lowest energy structure is the one there with the smallest formal charge on the atom. So lowest energy structure means the one with the smallest formal charge on the atom. The formal charge is a factor based on pure covalent view of bonding in which electron pairs are shared equally by neighboring atoms. So formal charges, it's a factor based concept, okay, purely based on the covalent viewing of the bonding, okay, how covalently they are bonded. Okay, and what is the sharing of the electrons between the neighboring atoms. Now next is the limitations for octet rule. What are the limitations for octet rule? Now, the octet rule, though useful, it is not universal. Even though the octet rule is useful, but it is not a universal law. It is quite useful for understanding the structure of most of the organic compounds, and it applies mainly to the second period elements of the periodic table. There are three types of exceptions on the octet rule. Now, octet rule, even though it is helpful in understanding some structures of most of the organic compounds, it only applies to the second period elements. Okay, and there are three exceptions which are there for octet rule. First one is the incomplete octet of the central atom. Now, in some compounds, the number of electrons surrounding the central atom is less than the 8. Okay, for some molecules, to attain their complete electronic configurations, they require 1 electrons. But the central molecules, okay, central atoms, okay, they show less than 8 electrons around them. This is especially a case with elements having less than 4 valence electrons. Okay, this exception is basically seen on elements with less than 4 valence electrons. For example, lithium, beryllium, boron, they have less than 4 valence electrons in them, so they won't show you any octet or 8 electron configuration on their outer shell. Okay, and these are basically the central metal atom or central atoms. This is the first exception, that there is the incomplete octet of the central atom. The second one is the odd electron molecules. So in molecules with odd number of electrons like nitric oxide NO, the nitrogen dioxide NO2, the octet rule is not satisfied for all the atoms. Okay, so when you have an odd number molecule, for example nitric oxide NO and nitrogen dioxide, it is NO2, okay, they doesn't satisfy the octet rule. Both of the molecules, okay, both of the atoms, nitrogen and oxygen, they doesn't complete their octets. Okay, so when there is an odd number molecule, the octet rule is not satisfied. Next one is the expanded octet. Okay, the expanded octet, elements in and beyond the third period of periodic table have apart from 3s and 3p orbitals, 3d orbitals also available for bonding. Okay, so the molecules from after the third period, okay, the elements after the third period, apart from 3s and 3p, they also have 3d orbitals available for bonding. In a number of compounds of these elements, there are more than 8 valence electrons around the central atom. Now octet rule is only up to 8 electrons, right? Valence shell should have 8 electrons, but when there is involvement of 3d orbitals or the d orbitals, this limit exceeds. There is more than 8 valence electrons which are available on the central metal atom for the bond formation. Now this is termed as expanded octet. Okay, because the octet is of 8 electrons. Now the octet is expanded. Okay, there is more than 8 electrons which are available in the valence shell. So obviously the octet rule does not apply in such cases. So octet rule applies only for 8 electron concept. Now here you have more than 8 electrons, so that rule doesn't apply here. Okay, and here are some examples, that is PF5, SF6. Okay, PF5 has total of 10 electrons around the p orbitals. P atom. SF6 has 12 electrons around the sulfur atom, and again H2SO4 has 12 electrons around the sulfur atom. Now, interestingly, sulfur also forms many compounds in which the octet rule is obeyed. In sulfur dichloride, the sulfur atom has an octet of electrons around it. So even the sulfur doesn't involve or doesn't follow octet rule, there are some compounds. Okay, sulfur forms some compounds which follow the octet rule. Okay, for example, sulfur dichloride. Okay, here it showed the following of octet. Now what are the other drawbacks of octet theory? These are the main drawbacks. Except them, what are the other drawbacks? Now next is, it is clear that octet rule is based upon the chemical inertness of noble gas. Basically octet rule, what it follows the inertness of noble gases. Means either by losing or either octet rule you are sharing the electrons, right? You are sharing or transferring the electrons. Now in both cases what you are doing, you are attaining a noble gas configuration. So it is basically based upon the chemical inertness of noble gases. However, some noble gases, for example xenon and krypton, also combine with oxygen and fluorine to form a number of compounds. Okay, even though they want to attain a noble gas configuration, some of the noble gases like xenon and krypton, they combine with other molecules. Even though they are completely filled stable molecules, they still form compounds with oxygen and fluorine. This is also another drawback of octet rule. This theory does not account for the shape of the molecule. It doesn't explain you the shape of the molecule. It does not explain the relative stability of the molecule, being totally silent about the energy of the molecule. Okay, so it doesn't explain you the relative stability, how stable a molecule can be, or what will be its energy. Okay, when it is combined with the molecule, what will be the energy of that molecule, what will be the relative stability, shape. It doesn't explain all these concepts. So these are the drawbacks of octet rule theory. So in today's part, we have seen the Kössel-Lewis approaches, their drawbacks, octet rule, drawbacks of octet rule. Okay. So thank you for watching my video. Please do like, share and subscribe to our channel.